Joris. Thank you, Joris, for accepting to talk so late in the evening. We really appreciate it. I'll ask everybody to turn their loudspeaker, their microphones off. And finally, to raise hands if they want to ask questions. I'll moderate and give you, I'll interrupt Joris between slides to take care of the raised hands. So Joris, please, we'll listen to you with pleasure.
Okay, thank you. So thank you for giving me the opportunity to give this Zoominar. So the title of my talk, you see it all, it's partition functions of paraboson and parafermion systems. It's work that I have done in collaboration with Nelly Stoilova from Bulgaria, and in fact we've had a long-term collaboration already for many years, and we've worked on different topics as well. In between, we've always come back from time to time to these problems of related to paraboson and parafermion systems. And the topic I will talk about today, is about the problem. Where we basically want to translate the new mathematical results we obtained over the last few years. We try to translate them back to physics, in particular particle statistics or thermodynamics. Although we are not at all specialists in this, we thought it would make sense to try and make this translation. On the other hand, you should know.
Yes. I'm not sure if I'm the only one having a problem, but when you talk, there's a lot of statics. Again, just now. So I don't know if you could try maybe to speak a little closer. I don't know how to solve this thing, but I'm just letting you know. And at the beginning, before 3:30, when we tried, when we were only 2 or 3, there was not such a problem. So let's see how it goes. Go on, but there's a little problem here.
Okay. Could it help if I actually close the video of myself and just have the sound?
Curiously, just now it was perfect. So why don't we try to move on and see if, and if not, we'll try closing your video. But as for now, it's okay. Okay.
I'm talking now a little bit closer to the screen, in fact.
Sounds good.
Yeah. So anyway, this talk is based on a paper which will be published. I think it is already published last week in Physics Letters A, and this is the archive reference. So before I say something about parabosons, parafermions, let me just give you one slide on bosons, fermions. So there's the usual notation for commutators, the usual notation for anti-commutators with curly brackets. And if you consider a system of, say, n pairs of Bose operators, bosons, creation and annihilation operators, Bi plus or minus, these should satisfy classical relation that is given here. Then it's easy if you also assume a certain conjugacy relation to construct a Fock space, and Fock space is characterized by a unique vacuum vector and by these relations, as we all know. So that is like the ground state of your system, and then you have basis vectors constructed as follows here. So these ni's and 1 and 2 and so on can be considered as occupation numbers, and they can assume any non-negative integer value. And for each set of such non-negative integer values, there is a corresponding quantum state, basically. So is the sound still right, Sivan?
Yeah, yes, it is. So far, so good. Let's move on.
All right. And then the other well-known system is a system of m pairs of parafermi operators, Fi plus or minus, satisfying an anti-commutation relation as given here. All others are 0. And in this case, there's also a unique vacuum vector for your Fock space, characterized by this relation here. And the construction of the space is the same, essentially as what is written here, except that these occupation numbers take the values 0 and 1. So these two algebras, basically, the algebra of Bose operators and Fermi operators, are characterized by quadratic relations, commutator or this anti-commutator. Now, let's now move, this is all part of the introduction. So let's now move to what are called paraboson operators. It's a very old subject, introduced first by Green. So we'll call the operators again, but with small bj plus or minus. J runs from 1 to n. And these are characterized by triple relations. So combination of anti-commutator with the commutator. And then I've not written all of them here, but if you take the usual conjugation, you use the other ones. And these relations can be, all of them can actually be summarized in one line if you write it in this way. But then, of course, these psi's, etas, epsilons should be in the right-hand side interpreted as, the plus or minus should be interpreted as plus or minus 1. Now, in this case, there is not a unique Fock space, but there are several Fock spaces, and they are characterized by a number p. This p will be a positive or non-negative integer. So if we assume same conjugacy relation, and again that there is this condition that it's annihilated by the bj minuses, then this condition on its own is not sufficient to have a unique vacuum. And that's the reason that other relations have to be introduced. And they showed time many years ago that this relation is necessary to have a unique ground state, unique vacuum. But p is just a positive, non-negative integer. And if you take p equals to 1, then the relations of these paraboson operators in this Fock space reduce to the ordinary boson relations. So this satisfies the usual commutation relations for bosons. But this is only in the case that p equals to 1. And therefore, the other cases are extensions of this, and one speaks of, say, paraboson systems of characteristic p for general p. Now here as well, one can introduce a set of number operators, call them ni hat, introduced as follows. And a quantum state, psi, say, is again a common eigenstate of these number operators with eigenvalues ni. These ni's are again occupation number, but in this case, for parabosons, for example, we'll see this later, these occupation numbers are still arbitrary non-negative integers, but it's not like in the boson case that if you have a set of occupation numbers that the corresponding state is unique. No, there are multiplicities appearing, and these are in general not easy to understand. So the same story more or less holds for parafermion relations. So m pairs of parafermion operators, fj plus or minus, also introduced at the time by Green, again introduced by triple relations, not quadratic relations, but triple relations as follows. The Fock spaces, I've called them now WP, are also characterized by a positive integer p. This annihilation for the vacuum is not sufficient to have a unique vacuum. There should be more relations, and they are given in the following line here. And just as for the paraboson case, if you take p equals to 1, these parafermions in this representation, these operators satisfy the same relations as the ordinary fermion relations. But this is not the case for other values of p. But again, one can introduce a set of number operators, commuting number operators, I should say. It's not so hard to show that these commute. And the common eigenstates of these are, again, the states of the system. And in this case, as we will see, these occupation numbers can take values not just in the set 0 or 1, but in the set 0, 1, 2, up to the value of p. And they can still... Yeah.
Sorry, Joris, there's a hand raised.
Yeah.
John, you want to ask?
Yes, just very quickly. So the ordinary F's and B's can be realized either as exterior operators on an exterior algebra or as derivative or multiplication operators on space of symmetric functions. What is the corresponding realization of these para F's and B's?
I'll come back to your question in 2 slides. Give me 2 slides and then I'll say a word about it. If I forget about it, remind me. But in 2 slides, I'll say something about the algebraic structure, and then it'll be clear how they can also be constructed, basically in the tensor product of an algebra, OSP, or an orthogonal algebra, tensor Clifford algebra. There is a construction that is already also known many years. But okay, I'll come back to this when we are that far. Okay, I'll continue now. Anyway, the interest in parabosons, parafermions, it's a very old subject, and interest has always been there, but somehow they never had a great breakthrough, I should say, in physics. And most of the work on parabosons, parafermions was really done by in mathematics or in mathematical physics. But although they never had their great breakthrough, the interest never disappeared. And I've just listed here some recent papers that still use them in various contexts. Okay, now I've introduced these relations as just triple relations, but it's also known already a long time that there's a deeper algebraic structure behind it. And for the case of parafermions, this is also known already from the 60s, and they realized at that time that the Lie algebra generated by these 2m elements, paraboson algebra, so subject to these relations, is just Lie algebra SO 2m plus 1. And the Fock space then corresponds to an irreducible representation with this lowest weight minus p over 2 minus p over 2 and so on. And so it's in this context maybe that I can come back to the question of Hannah. So what you can do is you can actually go to the Lie algebra SO 2m plus 1 times p, and take the ordinary Fock space, ordinary fermion Fock space in there. And in that ordinary Fock space, it's possible to give a very simple realization of these parafermion relations. Okay.
But I asked what the operator is. How do you define it?
Well, it's hard to write it down, but it's essentially, if you think of an operator, and if you think of your ordinary boson, or your ordinary boson Fock space or fermion Fock space, in the case of boson Fock space, for example, your operators are just multiplication by a variable or derivative by a variable. And so for the paraboson operators can be written as a sum over such multiplication or derivation multiplied by essentially by Clifford elements. And you the sum goes over an index that runs from 1 to p. Okay, I can point out a paper where it's given very explicitly, but it will not be in my slides here.
So p has to be an integer.
P is an integer, yes, a non-negative integer. Okay, so for the paraboson, sorry, for the paraboson operators, it was well found out, say, a number of years later when Lie superalgebras became popular, that the algebra generated by 2n by these paraboson elements, Bj plus or minus, considered as odd elements of a superalgebra, they just generate the simple Lie superalgebra OSP 1 to n, the orthosymplectic Lie superalgebra, and the Fock space is then an irreducible unitary representation, infinite dimensional in this case, with lowest weight p over 2, and so on. So in this case, it's infinite dimensional. Okay, so that fixes, or that gives a relation with the algebra, and the representations of these algebra. Now, really, I'll say a few words now about what we think that physicists are interested in if they want to use these n paraboson systems or n parafermion systems, for example, in a thermodynamical context. What they are interested in is what is called the grand partition function. And this is, I'll just write down this formula here. It's a sum of what is called the Gibbs factors with respect to all states of the system. So in our notation, it's a sum of, say, in terms of certain variables, x1 up to xn, up to these powers, these occupation numbers, and the multiplicity of the corresponding quantum states or basis factors for this multiplicity is in front of here.
Joris, may I interrupt you? Pavel has a question.
Yeah. I don't hear a question.
Pavel, you have to open your... Okay.
Okay. Can you hear me?
Yeah.
Yes, yes.
I just wanted to ask about this relation to a Lie algebra. Is this the only example, or is that always so?
Sorry, I didn't catch the
relation between the parafermions and the Lie algebra.
Yes.
That you showed us 2 slides ago.
Yes.
Is that a universal feature, or is that only in this case? This SO2M1 subject to the triple relations. Is this the only example, or does that happen for other Lie algebras?
For the triple relations that are defined as they are for parabosons and parafermions, it's SO2m plus 1 and OSP 1 to n, that's it. But for other Lie algebras and also even Lie superalgebras, you can also give a set of generators that with particular triple relations that define your simple Lie algebra or simple Lie superalgebra. That has also been done, but they become a bit more complicated. And these other triple relations for Lie algebras or Lie superalgebras, I don't think they have ever been used in any physical context, but it has been done.
So I'm really asking whether this triple relation gives more than the fact that you have an SO2M1 plus 1 algebra and representation.
Well, in this case, if you stick to the triple relations that we started with, it's SO2M plus 1 or OSP 1 to n, that's it. That's all you have.
Okay, thank you.
Yeah. Okay, so anyway, we are here, so I think this is not really my background, but if you work in a thermodynamic context and particle statistics, then these xi's are of this form: exponent mu I minus epsilon I divided by tau, with some fundamental temperature, some chemical potential, some energy of, say, the particles on orbital I, whatever system you're working in. Now, the interesting point really here is that people, if you look at this formula in this frame, is, well, all people in representation theory will recognize this. This is really just the character of a representation, because after all, these occupation numbers, and 1, 2, up to an n are the coordinates of the weight of a state or a basis vector, and together with the multiplicity. So that's just the character of the representation. So anyway, if we have this grand partition function, then people can deduce a lot of other statistical properties, thermodynamic functions from it, like entropy, heat capacity, some particle distributions, and in particular, for example, compute the logarithmic derivative, the average number of particles on an orbital, or the average number of particles in the system. And it are such things that we will show some examples of now that we have been able, during the last couple of years, to get new and interesting characters of the representations that we will be dealing with here. But before I can do that, I have to turn to a mathematical intermezzo and introduce some combinatorial objects that some of you or most of you might know, but still I'll go through definitions, basically. So first, the partition. I think probably we all know that it's a sequence of decreasing integer numbers. The weight of the partition is the sum of these numbers. The length of the partition is, well, the number of non-zero numbers here. And a partition is usually characterized or illustrated by what is called its Jeugt diagram. For example, the partition 5, 4, 2, 2 is characterized by this Jeugt diagram with 5 boxes on the first row, 4 on the second, 4 on the third, and 2 boxes on the last row. And if we add zeros to these partitions, it's the same partition. We don't worry about that. So for any partition, once you have this Jeugt frame, it's easy to see what is called the conjugate of the partition. And this will be noted by lambda prime. And the conjugate is just so the reflection of this diagram. In other words, you count the first row here becomes the first, sorry, the first column here becomes the first row of your conjugate, and so on. So this is now 4, 4, 3, 3, 1. So if I take a box in the Jeugt diagram, and I refers to the row index, counted from top to bottom, and J refers to the column index, counted from left to right, then we will be using two known objects. One is called the contents of the box, which is just J minus I. So it's a number which is a 0 on the diagonals. It has the value +1 here, value +2 there, and so on, and negative numbers below here, nothing special. And the other one is defined as follows. It's called the hook length of a box. And what it actually means is it's really just the hook length. If you take, for example, this corner box here, then what you do is count the boxes that are formed by this box in the hook. So it's 1, 2, 3, 4, 5, 6, 7, 8. So 8 is the hook length of this box here. And for each box, for this box, for example, that I'm showing here now, the hook length is 2 because there is nothing to the left and there is 1 below it. Okay, so these are very known definitions that we will need. The next definition is not so common, but it's also a very old notion. That's the Frobenius notation of a partition. And what you do for that is you first sort of cross the number of boxes that are on the diagonal of your Jeugt frame. And then you sort of look at the arm lengths, and arm lengths are the number of boxes to the right of these crossed boxes. So in this example here, the arm length of this first cross is 1, 2, 3, 4. The arm length of the second box is just 1, 2. Arm length of the third box is just 1. And then you also look at the leg lengths of these crossed boxes, and that's the number of boxes below it. So that's 1, 2, 3. That's 2 and 0 boxes below it. And then you denote your partition in the following way, as on the top, the arm lengths, and on the bottom, on the top, the arm lengths, and on the bottom, the leg lengths. And that also characterizes your partition. It's a different way of denoting it. And in this case, for example, if your partition is so-called self-conjugate means that it's equal to its conjugate partition. It just means that these AIs and BIs in the general notation of Frobenius are all equal to each other. Each AI is equal to a BI. Right. Now, these partitions, for us, they're important because they can be used in various contexts, but for us, they will be important because they are used as labels of the ring of symmetric functions in a number of variables. And this ring of symmetric functions with integer coefficients, I should say, has many bases. The standard reference or the standard book for this is the book on Macdonald on symmetric functions. And the most interesting bases are the bases of sure functions or sure polynomials. I've given just one definition here with a van der Monde determinant in the denominator and another determinant in the numerator, but it's a symmetric function. So I don't have time to go through all properties and all identities, but say apart from the fact that they form an integer basis for your ring of symmetric polynomials, one can also have many other interesting identities, in particular infinite series identities, and this is known as the field of S-function series, and some of them were already known to Cauchy, Littlewood, for example. If we start here from the right-hand side and take the series expansion of the product of overall 1 minus xi, 1 minus xj, xk in the denominator, then what you get is a sum of all sure functions summed over all possible partitions lambda. So that's the sort of field that many people have been working in. And this is the last combinatorial thing that I will need later on. An interesting specialization occurs if we take in this symmetric function all variables equal, say x1, x2, let's put them all equal to x. Then this symmetric function, the sure function with label lambda, which is a homogeneous polynomial in general of degree the rate of lambda, then just becomes a monomial, x to the power lambda. And the coefficient in front here has a nice expression where the hoop lengths appear and where the contents of each box appears. That's a nice identity that I think one can find it in the book of Macdonald's, probably also in other reference works. And another interesting specialization of your sure function is when these variables, when their consecutive ratios is constant. So when they take the form x, q times x, q squared times x, and so on. So also in this case, your sure function or sure polynomial becomes just a monomial, x to the power the rate of the partition. And what is then written here is essentially, well, you could see it as the q number of the number that appeared before here. Because of course, if you take limit q equals to 1, you get back to the previous specialization. And there's still a q factor in front. Okay, so these are the things that I will need. And let's now go back to the n paraboson system first. So in this case, I'm not going to give, say, proofs or details of the work that we have done and that others have done. But in this case, the partition function, which is then based on the character, of course, of the n paraboson system of order p, is now given. Well, you can write it as an infinite sum over all sure functions lambda, such that the length of lambda is less than or equal to this p. And remember, p is a certain choice you make, 1, 2, 3, or so on. Okay, so this was also known by others, but somehow this is not a proper form of your, well, it's a correct form, it gives character, but it's not as we say, it's not a character formula because it's not written as a generating function in terms of these variables. And
Joris, may I interrupt you? John has a question.
Yes.
Well, actually, it's a remark. That's a tau function, and it has a matrix integral representation as well. It's the tau. I mean, all tau functions are linear combinations of Schur functions,
Yeah.
in which the coefficients for these content products. But you have coefficients 1, which means that the thing that forms the content product is just the number 1. That's what you put into every place in the Young diagram, and that is a particular case of a KP tau function, and it also can be represented as a matrix integral.
Okay, I didn't know that. I would like to see it because, okay, soon we'll come to another expression for this, and maybe you even have more interesting remarks at that point. Okay, so for p equals 1, of course, this is easy to rewrite it in general.
Sorry, just an addendum to that comment. P, the number p in the matrix integral is the size of the matrices.
Okay.
When you have a tau function that's a matrix integral, the length of the partitions that you sum over are always limited to less than or equal to the size of the matrix.
Okay.
Okay, sorry.
Yeah. Okay, I'll take a note of this because it's not something that I knew about. So the case p equal 1 and p larger than or equal to n, as this case we've seen already in this Cauchy-Littlewood expression. P equals 1 is also simple, but for the other p's, a proper generating function or good formula was not really known, and I think we were, at least I hope we were the first to come up with it in some years ago. And it can actually be written in the following form. So a particular denominator, the same as in the formula of Cauchy-Littlewood, but then some polynomial expression in the numerator, which we call En. En refers to the number of variables, and P to the particular value of P that we have chosen here, to the order of statistics, basically. Now, what does this E and P look like? What is it? Well, it's a polynomial. It's an alternating sum because there are plus or minus signs of, again, particular Schur polynomials as eta of x. And what etas do we sum over? Well, we sum essentially over all self-conjugate partitions. So where your arm lengths A1 are the same as your leg lengths A2 and so on, but to which you add P extra boxes to the legs of your partition. So in Frobenius notation, they are of this form. And this C eta is just the number that you compute here in order to determine whether it's a plus or minus sign in your alternating sum. So definitely at first sight you think, okay, this might also look like an infinite sum, but it's not, because your number of variables is finite. So even if you would sum just over the self-conjugate partitions, it's already a finite sum, because as soon as the number of rows in your partition increases, is larger than n, the Schur function is automatically 0. So it's a finite sum. And in general, for certain examples, it's always very easy to compute. You just list your self-conjugate partitions, add these p's to it, and soon this sum ends because the length of your partition is becoming larger than the n value that you are working with, and that's a way to compute them. Okay, now if we go to, well, there are some on the slide, there are a few simple examples. If P is 1, then this expression, it's not so hard to prove that it can be rewritten as the expansion of this product. If P is equal to n minus 1, remember you have to add n minus 1 boxes to the leg, so that only one partition can survive, and you have a very simple short expression. And for any p larger than n, you have no partitions left. You just start with one, and that's it. So these are really simple examples, but they give them, for example, these explicit expressions for this grand partition function. And this one, first one here, coincides, for people who know about it, of course, with the grand partition function for an ordinary n boson system. So far we've been looking at, we've done in general, and we can go to specific values of p. Now let's go to a specific case where we say, well, if we are in this interpretation of particle systems or statistical physics, and these I refers to the orbital that particles are sitting on or heaving on, we can now go to the case where we have, so to say, identical energy levels. So let us assume for a while that all these orbitals of our n paraboson system have the same energy, same chemical potential. So all these variables, x1, x2, are the same, particularly this value. Now we come to these specializations that I've talked about before. So for p equals 1, there's nothing special. That's the, this is here just the grand partition function. By the way, I've denoted the cases with identical energy levels. I've put this wedge here on top of my functions. So that's the grand partition function. And it's easy to compute, in this case, for example, the average number of particles in the system given by such an expression. And I've listed here also the other special simple cases, but of course, we can, since we have this general expression in terms of this alternating sum E that I've shown you before, we can do this for any value of n and p and compute, for example, the average number of particles. Let me just, in one case, show some plots of this. So what is plotted here, it's basically it's the distribution, the average number of particles. In terms of this variable y, and our x was e to the power minus y. This is for a certain n that we have chosen, and then we plot it for p equals 1, 2, 3, 4. But as you remember, as soon as p is larger than n, so as soon as p is n and larger, then there's no longer a change in the partition function, so also no longer a change in the average number of particles. So the fourth line starts labels, in fact, all other values of p. Case p equals 1 corresponds to the, well, people are familiar with this, to the ordinary boson sign distribution function, and for other values of p, it's a similar shape but slightly shifted. But the interpretation is still more or less the same. The smaller the energy, so to say, the higher, the more particles there are on average in the system, or otherwise said also, high temperatures correspond to more particles, low temperature correspond to fewer particles. But okay, I'm not a physicist, but at least I wanted to show some plots because they are very familiar to what is known in general for people who are working in this context. We also considered a second case where the n orbitals are no longer have the same energy level, but we assume that the energies of the n orbitals appear with a fixed gap delta, so they are equidistant, right? So epsilon I is your first energy plus I minus 1 times a fixed gap delta. Okay, in that case, these variables xi really becomes just a fixed x corresponding to the ground orbital multiplied by q to the power I minus 1, which means that we are in this second specialization where we know a lot about the Schur functions. So the notation for the second specialization with equidistant energy levels is now denoted by a tilde. So this partition function is just the general one we had, where xi is substituted by x times q to the power I minus 1. And E tilde is just our ordinary E tilde, again under this substitution. And really these expressions, because precisely our Schur functions, also our Schur polynomials also just become monomials in this X. They also simplify a lot. I've written an example here, but it's not the purpose to show you many examples. But it's almost straightforward to compute these alternating sums, these all finite alternating sums, and then write down, say, the corresponding partition function. Let me also, in this equidistant energy level case, show you one plot here. So I've shown you before that if once you have the grand partition function, you can compute things like the average number of particles on a fixed orbital, Li, where I runs, say, from 1 up to n. We've taken here n equals to 5, so there are 5 orbitals, equidistant energy levels. Of course, if the energy would be the same on all of them, then the average number is also the same on all of them. But in this case, that is not true. It's related. The gap is represented by this variable q, and what you see here again in these plots is, so to say, we see it as the population of the parabosons on orbital I. If we are in this point where q is equal to 1, q equals 1 means that the gap is 0, so that all energy levels are really the same, and then all the distribution of these levels is also the same. And on the other hand, in this area, say the energy or the gap between the energy level becomes larger and larger. So if the energy gap is really extremely large, all particles are essentially on the lowest energy, and sort of in between you always see that most particles are on average, most of them are on the first, then second, down on the second, then on the third, on the fourth, on the fifth. The occupation number decreases according to the height of the energy level. So that's our way of interpreting this. And these functions are now easy to compute because we have explicit expressions for these partition functions. Okay, before I come to some more general notions again, let me just briefly also now go through the case of the M parafermion systems. So in this case, the grand partition function is now the following sum. It's the sum of all Schur functions in M variables labeled by partition lambda. In this case, the sum over all lambda such that the length of lambda prime is less than or equal to p. In other words, the number of columns should be less than or equal to p. If you remember what I said, Schur function, as soon as the length of lambda is larger than m, the Schur function is automatically 0. So combining both things that I've said here means that this is now a finite sum. It's a finite sum of all partitions of length at most m and of width at most p. So inside a rectangle, an m by p rectangle basically. So of course it's a finite sum because after all, This case is much simpler. It's a representation of a finite dimensional representation of an orthogonal Lie algebra, and characters here are well known. You can use Weil's character formula or whatever you want. So there are many known expressions. So in a way, you would think there is nothing much new to be found here. But in fact, we did also work and we did find a new alternative expression for this partition function, or this character, if you want. And it's again something like this, similar form. This top EMP0, you remember in the other case it was N0P, now it's MP0. It will soon become clear why this notation is chosen. And denominator is of a similar type. By the way, for people who are very familiar with Weil's character formula, this is not Weil's character formula. In Weil's character formula, there would be more denominators here. There would be also, say, a product over factors of the form 1 minus xj times xk inverses. There would be other things here as well. Anyway, let me also explain in one or two words what this finite expression at the top here is. It's very similar to what we've seen before. It's a sum over all partitions SU, and almost again a sum over all self-conjugate partitions. But in this case, it's the self-conjugate partitions to which P boxes are added to the arms of the partition, not to the legs. Okay. For example, if P equals to 1, this expression, you can find it back in some books or papers on S-function series, and then it can be rewritten in the following form. And then the partition function becomes just product over all 1 plus xi's, and this is nothing else but the ordinary grand partition function for an M fermion system. So for P equals 1 or P larger than M, you usually find nothing new. It's for the intermediate cases, P between, say, 2 and M, that these expressions are interesting and have, as far as we know, not been constructed before. Right. Also for M parafermion systems, we just
before you started this slide, John would have a question again.
Yeah. Or maybe a remark.
Yeah, I'm just curious if the thing is positive. Is your partition function necessarily positive?
The expansion of the partition function, yes, it's always positive, definitely.
But your x's, is there some bound on x's or something? E is the partition function, or it's the...
No, E is not the partition function. E is, so to say, the numerator,
that's the numerator. Okay,
numerator of your partition function.
Okay.
And in your E has alternating signs, but the partition function as a whole, you see it from the above expression, is always positive.
Okay, thank you.
Yeah, yeah. Okay, so also in this case, we did the same two exercises if we want. Consider first M parafermion system with identical energy levels, which means that all the x's take the same value, and we use similar notation, a wedge on these, put a wedge on these partition functions in order to express them. And so we have in this case also computed, or it's easy to plot things like, for example, the average number of particles on an orbital. I think I have one plot for this. Yes, this is for the M equals 4, so 4 parafermion system with identical energy levels. And we've considered 5 representations, P1, 2, 3, up to 5. And we've plotted the average number of particles on an orbital, which does not depend on I, because the the energy levels are identical in terms of the same variables as people always do. So for p equals 1, it coincides with the Fermi-Dirac distribution function. So your number of particles, so average number of particles sits between, well, 1 and 0. But for other values of p, there are different interpretations, and your average number of particles sits between 0 and p. Okay, which is a peculiar feature of parafermion systems. And we did also the similar exercise for parafermion systems with equidistant energy levels, where your xi's are of this form, x times a power of q. And because we can again simplify the Schur functions in our numerator expression extremely, which means it's also easy then to compute other things from this partition function, like average number of particles, like number of particles in the system, and so on. This is, as an example, again, a plot for a particular value of m, a particular value of p now. P is fixed, but now it's equidistant energy levels. So we have here m, which is 5 energy levels, and we've plotted the average number of particles as they came out of this grand partition function. So I think I should not go into the details of these plots, but I think to end, let me say a few more things about the mathematics, or some mathematical remarks, or some remarkable properties which link the two cases really. So remember, in our partition function, or in our character formula, if you want, we had certain numerators, and I will concentrate now on the case of identical energy levels. So all x's are equal. So here we had sum over Schur functions, self-conjugates, but with p boxes added to the legs. Here we have self-conjugate partitions, but with p boxes added to the arms of the partitions. Right. Now, of course, if we would look back to this specialization that I've given in the beginning in the mathematical intermezzo, then from that expression, you remember the Schur function specializes just to x to the power, the weight of lambda, with some factor in front. And in that case, if you look back to this factor in which contents and hook length appear, it's fairly easy to see that this s with a number of x's, lambda, and s lambda prime with a number of x's, and these two here, the etas and the mu's, are conjugate to each other because you add p numbers to the legs or to the arms, that they actually are the same, provided the number of x's here is of the form, well, say an integer plus the length of lambda, and the number of x's here is the same integer plus the length of lambda prime. I mean, to see that it's really the same, you should go back to this formula that I've shown you before there. So because of that, it's a simple exercise to see that these numerators, that they become the same in this case of equal x's or identical energy levels, and this identity holds. And then if we also include the denominators of the partition functions or the characters, we have the following identity. So the character or the partition function for a paraboson system of order p, of an n paraboson system, can be written as say the partition function of a parafermion system with n minus p parafermions of order p and some extra denominator. So it's a quite nice coincidence here of these partition functions. And because of that, we said, okay, let's now concentrate it on those for the parafermion system. If we have these, we can use those of the paraboson system as well. And we did that, and that's the second property that I can add here, but it's a property which we haven't finalized really, but we started examining these partition functions for, say, for fixed values of p, where it was not known, say for p plus 2 and arbitrary m. And then after some examples, after some calculations on, it was fairly easy to see that it can be written in the following explicit form. The coefficients that appear here are known as Majorana numbers, and they also have many other combinatorial interpretations. And also for p equals to 3, we managed to find some other explicit forms of these partition functions, always in the case, I should recall you, of equidistant energy, of identical energy levels. But we have not managed to sort of simplify them for larger values of p, at least not yet in closed form, although we have a form for it, but not in closed form as we have obtained here for p equals 2 and p equals to 3. So at least for us, it was interesting to have these results. Maybe I should also mention, because those of you who are, say, very familiar with representation and character formulas also have realized through the time of my talk that what I'm doing here, when I specialized to identical energy levels or to equidistant energy levels, is really take certain what people call specializations of characters, but they are different from what is known as the principal specialization of a character. Because for principal specializations of characters, there are formulas in the book of Katz that really give you a very simple form. But here it corresponds, in both cases that we have been dealing with here, it corresponds to other specializations than principal specializations of character formulas. So, yes, with this slide, I've come to the final slide of my talk. So I've started really with very old team algebras characterized by a set of generators satisfying a set of triple relations, in particular then the triple relations that characterize parabosons and parafermions. We find their Fock spaces, and we've realized, okay, the algebraic structure is related to a Lie algebra or a Lie superalgebra. The Fock spaces are related just to certain irreducible representations of an orthogonal or a orthosymplectic algebra. Then in more recent years, and this was so the work that has been continuously going on in collaboration with Nelly, we've obtained new character formulas for these spaces, for these Fock spaces. And there are these new formulas that are, so to say, in ideal form to get something more for the grand partition functions, because there you want them as written in the form of generating functions, so to say, so that you can easily deduce these other statistical properties from them. So these new formulas allow us to analyze statistical or thermodynamical properties of paraboson or parafermion systems. I've said that really these specializations that we are interested in also correspond to specializations of characters, different from the so-called principal specialization. And I think there is more combinatorial work to do to get these expressions in even more explicit form if one wants to do this. Okay, that's, I think, the end of my talk, and that's more or less perfect timing.
Indeed, perfect. Thank you very much, Joris. So I'll invite questions. Again, you may raise your hand if you want. John has one, as usual. Go ahead, John.
I may be wrong, but I suspect that, I'm not sure about the parafermi case, but the parabose partition functions that you were listing, I suspect that maybe all, or at least some of these can be obtained as degenerations of the Harish-Chandra-Itzikson-Zubair integral.
Degenerations of, sorry, Harish-Chandra?
The Harish-Chandra-Itzikson-Zubair integral. This is famous integral over the unitary group of the exponential of, well, anyway, it's a very famous integral.
Yes.
And there's an explicit expression in terms of ratios of determinants, but it's for distinct eigenvalues, and in fact, two sets of eigenvalues. So you have one, you've got x's only, not x's and y's, but it's possible to take limits in which these eigenvalues degenerate, as you were doing. And I suspect that some of these degenerations will actually reproduce your partition functions.
Okay, that would be an interesting thing to do and try and see. But I have not say these characters that I've shown in this talk. I've certainly the characters themselves, especially for the paraboson case. That was work we did already well, almost 10 years ago. And I've shown them in a number of seminars and talks already, but no one made this comment. I mean, I remember, for example, that Victor Katz was present in one of the talks, and he was interested in the form. He did not make this comment. So you can be right, but I'll have to look at it in more detail to see whether it's really corresponds to that. If it does, then well, okay, then it's even more interesting, I would say.
So what is pretty, I'm pretty sure, is that these sums, for instance, over the Schur functions, when you have all the x's equal or different, even different, that these are indeed in the integrable language tau functions of a very special kind. They're so-called hypergeometric tau functions. They all have coefficients which are of content product type. And the Itzikson-Zubair integral is an example of one of those things. And even the Cauchy-Littlewood formula is very closely related to these things. So, if you want, I can send you some literature.
Yes, please do.
Luc?
Joris, first, thank you for your talk. It was particularly interesting to note that the connection you made towards the end between your partition function, and it made me recall a paper or some work by Peter Surani. I don't know if you know it, and I wonder then, this is my question, if it's what you found is related, because he had looked at thermodynamical properties of P equal to paraboson. And he had found that this is equivalent to a mixture of boson and fermions. Does that connect to what you're finding here? I was just curious about that.
I don't know the paper you're talking about, but I would be surprised that it's connected to this. Let me go back here to this here, because from what you describe, it looks more as if, I think, and this is also something that people have done, is they have looked at systems in which paraboson operators and parafermion operators appear together in a combined form, and then this is related, as you may also know, to particular representations of OSP 2n plus 1 2n of a bigger orthosymplectic superalgebra. So it sounds to me more like something like that. But again, I don't know the paper.
Okay.
I would have to look at the
in the past century, for sure.
Yeah.
And maybe just a simple question: could you Q deform all you've said?
Yes, but well, not. I'm not sure all I've said, but definitely the say for the algebras SO2n plus 1, OSP 1 to n, there are Q-deformed. There are the Q-deformed algebras. Definitely, you can try to go to the similar set of generators like you do for SO2n plus 1, OSP 1 to n, and then you find also triple relations in which parameter Q appears. But this has been done also in the past century, and the relations themselves look quite well, okay, quite horrible, I would say. I've never been a fan of doing that, really.
But it could be interesting in terms of symmetric functions, though.
Yes.
You get Hall Littlewood or something like that.
Okay, you're thinking of that Q gen. Yes. Okay, I was thinking of the Q generalization of the actual relations of the paraboson parafermion relations. Okay, then one would have to look at the corresponding character in which Q numbers appear. Yeah, maybe it gives like Q versions of these Schur polynomials. Could be, yes. I don't know. It has not. I don't think this has been looked at.
Thank you.
Joris, well, we lost our lecturer. Okay, we lost you for a little while, or it's me. Happy, Luc?
Yes.
Yeah. Okay. So Pavel has a question. Go ahead, Pavel. Pavel, you have to open. Okay. Wait.
Okay.
Okay, go ahead, Pavel.
I have a sort of philosophical question. There's no doubt that bosons and fermions exist. Now, are parafermions, parabosons, just a convenient tool for calculating essentially mathematical relationships? Or is there any possibility that they actually exist? And if they do exist, how would we know? Is there any way that one can think of an experiment or suggest an experiment to discover whether they actually exist in nature? I don't hear you now.
I doubt I can give you a proper answer. This is more, say, for a question that should be answered by a physicist. As you know, I'm a mathematician, and all we see and all we can realize is that physicists are still using parabosons and parafermions in various constructions. But whether there is, say, a deep, how should I say, a deep fundamental physics behind it, I don't know. The only thing, and this is related to probably the first question that John asked, is that if you have, say, a system if you have a system of n times p, let's go to parabosons here. If you have a system of n times p ordinary bosons, you can, in that Fock space and with these ordinary boson operators, you can construct, using also an extra Clifford algebra, you can construct operators that satisfy the relations of parabosons. So in a way, one could say if you believe that bosons are fermions and fermions are there in nature, then you just sum over them, put in some Clifford elements, and then you also have parafermions and parabosons in nature. But okay, this is a way of, say, avoiding your question, and it is just a mathematical answer, really, rather than a physical answer to your question. But that's the best I can do.
Joris, is there something like your numerator capital E, but with the two last indices non-zero?
Sorry, which E? This?
Exactly. So you've presented us the E n semicolon 0p
Yes.
and p0.
Yes.
Do you have a p1 comma p2?
Yes, in principle, you could, I mean, you can define it as the sum over all self-conjugate partitions to which P1 boxes are added to the arms and to which P2 boxes are added to the legs. Right, you could do that, and that's how you can formally define it. And I think that is the origin of our notation here, because we thought at one point we can generalize then this notion, but we never found any context of where we could actually use it or apply it.
Okay, it would not correspond to a specific combination of parafermion and paraboson with satisfying some relations.
No, if you take combination and you look at corresponding representations of this bigger orthosymplectic superalgebra, you again end up with just one. If you wanted to have a unique vacuum vector, again, you end up with just one parameter P, and the only difference then is that you are working with Schur functions that are not that are supersymmetric Schur functions, not ordinary Schur functions, but supersymmetric Schur functions. Just one P appears here.
Okay, I think, Geoffroy has a question. Go ahead, Geoffroy.
It's more of a comment for Pavel, but if I'm not mistaken, in 3D, you can always reduce any system to a system of bosons and fermions. But when you look at confined system in 2D, you can have more possibilities in the statistics. So presumably, and we have observed that in some cases, not for parabosons, but particles obeying the braid group statistics. So technically, you could have experiments that are looking at the statistics of the excitation of a confined system, which would be best modeled as maybe parastatistics or other forms of exotic statistics, instead of modeling the full thing in 3 dimension and taking, you know, a limit of a 2-dimensional model.
Thank you, Geoffroy. There's no more questions, so I suggest that we thank our speaker. Joris, thank you very much for the talk. Some of the microphones are open, so thank you very much. It was extremely pleasant, and thank you again. Next week is Robert Brandenberger from McGill.